problems. So let's continue on here. Using a different setup today just because the tech decided to have a mind of its own today. Okay, so last class we introduced the idea of ionization energy. And I said it's important for you to be able to identify and explain these different terms. I'm in a different program. It looks different. Interesting. We can work with that. Okay. So ionization energy is the energy required to steal an electron away from an atom or an ion. As we go across the periodic table, we can see that on the whole, the major trend is that the ionization energy increases. As we go across the periodic table, the effective nuclear charge is getting stronger. The pull on those valence electrons is getting stronger. So you have to put in more energy to be able to steal an electron away from a smaller ion with a stronger effective nuclear charge compared to a larger ion with a lower effective nuclear charge. We can also see as we go down the periodic table, the ionization energy decreases. It's hard, you have to put in a lot of energy to steal an electron from a small ion, but as we go down the periodic table, there are so many electrons. Cesium here has 55 electrons. You want to steal one? Sure, it's a little bit easier because it's so big, it already has so many electrons. Those are the big trends that you need to know. But just at the end of last class, we identified that there are some anomalies where the trend is broken. For example, as we go across from lithium to neon, yes, the big trend is ionization energy increases. You have to use more energy to steal an electron from those atoms. But we have two highlighted anomalies. Let's look at the first one, beryllium and boron. If we look at the valence electrons for beryllium, it has 2 electrons in the 2s orbital. Boron also has 2 electrons in the 2s orbital and 1 electron in the 2p orbital. Well, if we go ahead and try to steal an electron from boron, we would steal the highest energy electron away, and that one is in a 2p orbital. It's kind of just hanging out there at a higher energy level all by itself. But if we're stealing an electron from beryllium, we're stealing it from a filled orbital where it has an upspin and a downspin, it's complete. It requires more energy to do that. So boron breaks the trend, but it does so because it has this electron hanging out at a higher energy level. It's easy just to come along and steal that one. Let's look now at nitrogen and oxygen and see if we can come up with a rationale, a reason for this anomaly as well. We would expect oxygen to have a higher ionization energy than nitrogen. Nitrogen is 1402, but oxygen isn't like 1500. That's what I would predict based on the big trend. It's 1300 and something. It's smaller. So if we look at the valence p electrons for these two elements, nitrogen has 3 half-filled orbitals, 1 orbital each in px, py, pz. Oxygen has 1 paired electron orbital and then 2 single ones. Ionization energy is when we steal that electron away. So for oxygen, we can see that we would be stealing that paired electron, leaving it with 3 electrons. For nitrogen, we would be stealing one of the half-filled orbitals. Remember when we were imagining sitting at the doctor's office and we had 3 two-person benches and people tend to fill up singly before they double up? For oxygen, it's had to double up. That person or that electron had to sit next to someone in the doctor's office on this squishy bench and they're a little uncomfortable. If you ask them, do you want to leave? You're like, yep, I'm out of here. So this electron is a lot easier to grab from oxygen because it's a little uncomfortable in that paired orbital. Of course, it doesn't have feelings, but it does take a little bit of energy to pair up electrons. So that's why we have this downtrend. That paired up electron, once it's removed, we have 3 half-filled orbitals. That's nice and stable. So that explains this trend anomaly here. Okay, so we've had ionization energy when an electron is stolen away, an electron is removed. Now we're changing gears, we're moving to our next trend, and we're on to electron affinity. Affinity means to like something or love something. This trend and this term is talking about how much that atom or ion loves getting an extra electron. The definition for electron affinity is the energy change, we're talking about enthalpy as the energy, when a gaseous atom or ion gains an electron. So now we're adding an electron. Remember, ionization energy was stealing an electron. Now it's getting an electron, and we're going to measure and say, Mr. Atom, how happy do you feel right now gaining an extra electron? And it tells us how much it loves having that extra electron. Of course, atoms don't have feelings, but they do have energy changes. The energy change often with electron affinity is exothermic. And you'll probably remember exothermic is when we have a negative change in energy. Energy is released, the product is more stable. An exothermic reaction is favorable. It tends to happen. So a greater electron affinity is when it's exothermic. In contrast, endothermic reactions have positive delta H values. That's not favorable because you have to put energy in to make that reaction happen. You're like, okay, I'll give you the electron and I'll put in some extra change on the side to make you happy. So these reactions, if they're endothermic, if they have a positive delta H, that means they have a lower electron affinity. So we want to be watching for those negative signs. Those are favorable. That means that atom is very happy to receive that extra electron. So we can start with a neutral atom of oxygen, add an electron, and we can see that this is an exothermic reaction. That means that it is favorable and it has a good electron affinity. It's really excited to get that extra electron. Well, if we take that O negative, add another electron, ooh, that is not favorable. This one is endothermic. It does not have a very good electron affinity. Now, this might be counterintuitive because you probably know we have lots of compounds in our world that have O2 negative as an ion. That O2 negative now has a noble gas electron configuration. We've been trained that that's a good stable thing, right? Well, we need to remember that this reaction is happening in the gaseous state. Once we take that O2 negative as a gas and it turns into a solid and into like a compound, then there are other interactions at work that make that more stable and make that a favorable reaction. But for here, we can see the energy required for each successive electron addition. Every time you want to add more and diverge from its original neutral state, it becomes less and less favorable. So that means more and more endothermic, less negative. Okay, we can look at our periodic table. We're looking at some of the main group elements, and we can see this electron affinity trend. We start with hydrogen, negative 72, and we can go all the way down to cesium with negative 45. As we're going down the periodic table, it's becoming less favorable. As we go up the periodic table, we can see it becoming more negative, which means it's a greater electron affinity. Why? Well, hydrogen, you give it an extra electron and it's like, wow, I only had 1 electron. Now I have 2 electrons. This is amazing. Thank you so much. This is an exothermic, very favorable reaction. You do that to cesium and it's like, oh, I already have 55 electrons. You're giving me another one? Oh, that's nice. Okay. As the atoms get smaller, as we go up the periodic table, they get more excited. Not excited. They get happier. They release more energy. They become more stable to get that extra electron. It has a greater impact on them. They just love that electron so much. Okay, let's go across the periodic table. We can see if we go from lithium, we're at like -60 there, carbon -110, fluorine -328. We can see they are getting more negative as we go across the periodic table, which means the electron affinity is increasing. We have a whole lot of love happening for electrons as we go up and to the right of our periodic table. Fluorine here has the greatest electron affinity. Why? Well, as we go across the periodic table, we know I've just lost the word. What's the term? The Z star. Effective nuclear charge is increasing. Those atoms are getting smaller, so getting an extra electron has a real great impact on them. Meanwhile, over here, they're larger, lower effective nuclear charge. Notice here that this arrow stops before we get to the noble gases. It gets more negative, more favorable, more exothermic, greater electron affinity as we go across the periodic table, except when we get to the noble gases. I'd like you to turn to the person beside you. You have 30 seconds to discuss why. And 3, 2, and 1. Who wants to give a reason for why the trend doesn't carry into the noble gases? Yes, go ahead.
Because of the full octet.
Yes, can you tell me a little more?
The octet's full, so it doesn't need any more electrons, and an extra electron would need another power level.
Excellent, very good explanation. If we add an electron to neon, that electron would have to go into the 3s orbital. Neon already has a filled 2s orbital, filled 2p orbitals. It's nice and content, it's filled. But that extra electron is added to a higher energy principal quantum number. That requires energy. That's not very favorable. So it doesn't follow the electron affinity trend. It breaks there because we'd be adding it to a higher principal quantum number. Okay, we need to know the big trends, but we also need to be able to have some explanations for some anomalies, like sodium and magnesium here. So I would like you to chat with the person beside you for 30 seconds. We can see sodium has a favorable electron affinity. That's exothermic. But magnesium doesn't. Why? Chat with the person beside you for 30 seconds. And 3, 2, and 1. Who has a reason? Thank you.
Because it has to go to p orbital and s is full.
There we go. That is the answer. For magnesium, if it gets an extra electron, we have to go from the filled 3s orbital to the, where are we? 3p orbital. We have to go to a higher energy orbital again, and that's not very favorable. So sodium getting an extra electron could have a filled 3s orbital. For magnesium would be 3s2, 3p1. That's not as favorable. So that's why we see this change in the trend again. That said, know the main trends best, but also be able to have an explanation for some of these anomalies. Okay, so we have done ionization energy, stealing an electron. Electron affinity, gaining an electron, seeing how happy it is to get that electron. And now we're on to electronegativity, our final trend discussion for today. Now, again, we need to know the definition for each of these trends, what they mean, and how they're different from each other. Notice now that it's a measure of an atom to draw a pair of electrons of a bond to itself. Previously, we were talking about atoms or ions in gaseous state. Now we're talking about an atom that has a bond with something else. So it's not all by itself gaining or losing electrons. It has a bond, and we want to see what those electrons are doing in the bond. Okay, so as we look here, we can see a whole bunch of numbers. These numbers are smaller. We can thank Linus Pauling for this numbering system. And it's a measure of the tendency of that atom to be an electron hog. We're measuring how good or bad it is at sharing shared electrons. Or any electrons, they don't have to be shared. How much does it want to draw those electrons? Is it good or bad at sharing? Okay, let's look. As we go down the periodic table, we can see the numbers decrease. We're going from 2 to 0.9 to 0.8. Electronegativity is getting smaller. As we go down the periodic table, those atoms are getting bigger. And it's those electrons in the valence shell are just further away. And so it's like, do you want the electrons over there? Maybe, sure. Versus, ooh, yes, I definitely want those electrons because they're nice and close to me. As we go across the periodic table, we can see the trend increases. Lithium is 1, boron is 2, fluorine has the very highest electronegativity at 4.0, the most electronegative atom. As we know, as we cross the periodic table, that effective nuclear charge is increasing, the size is decreasing. We have electron hogs over on this side of the periodic table. You have electrons, I want it. You have electrons, I want it. And it pulls those electrons in a bond closer to itself. But we don't seem to have any values for those noble gases. Anybody have an idea of why? Yes?
Is it because we don't find them in like chemical compounds together, like helium, neon, we don't find them, so then we won't know what the electronegativity for those elements are.
Excellent. You had a very good explanation. I don't think the microphone was on at the beginning. But yes, you are correct. These elements, helium, neon, argon, we don't really find them in bonding situations. So we haven't been able to measure. And so those numbers are irrelevant because they don't really participate in bonding. As we go down to the larger noble gases, they do participate in bonding sometimes. So we have some measurements for those. Good explanation. Thank you. Okay, so I have a question for you then. Chat with the person beside you. Predict which of these bonds would have the greatest unequal sharing of electrons. And 10 more seconds. And 3, 2, and 1. Okay, most people going for C, and I agree. Here we have the most electronegative atom on the periodic table. Not sure if technology is my friend today. But yes, fluorine is the most electronegative atom. It's being combined with an atom that is not very electronegative. Fluorine can definitely pull those electrons. That's in contrast to B, where we have fluorine and fluorine, two very electronegative atoms, but they're both the same amount of electron hog. They're both pulling on those electrons, which means those electrons are going to be shared equally. Which brings us into our next chapter. We now want to go from learning about atoms, separate entities, and bring them together to form compounds. And 3, 2, and 1. Okay, so we've gone from atoms and ions, and we know how to predict their trends and their electron configurations. And now we're going to take all of that knowledge and apply it to bringing atoms together. We're going to start to make different types of compounds and molecules. Well, first, we need to remember that only those valence electrons are the electrons that will participate in bonding. When we were writing out electron configurations, we learned how to identify those valence electrons, highest principal quantum number, n, and then the core was everything else. Now we're just going to be paying attention to those valence electrons. So hydrogen has only one valence electron. Fluorine, its valence electrons are in the 3s and 3p orbitals, and it has 7 valence electrons. And you may have learned how to draw some dot diagrams showing the electrons as dots around this. Well, if we think about the electron configuration for hydrogen and that for chlorine, 3s2, 3p5, these two atoms can come together and share their electrons. One atom from hydrogen one electron from hydrogen and one from chlorine can form a bond, and we could draw them side by side as well. Maybe we'll leave it like that. A pair of electrons can produce a covalent bond. You can draw them as dots, but more often we draw them simply as a line. And you can imagine that that line has one dot at each end because it takes 2 electrons to make that covalent bond. Notice that we didn't draw in the core electrons. We're only paying attention to the valence electrons. So sometimes electrons are shared. 2 electrons sharing can form a covalent bond. But if the atoms aren't very good at sharing, we're going to form a different type of bond, and that is an ionic bond. How do we know if we form an ionic bond or a covalent bond? Well, we have a couple different methods to be able to predict which type of bond we're going to have. We've just learned about electronegativity and how it increases as we go up and across the periodic table. Atoms on the periodic table that have low electronegativities, usually the metals on the left and middle-ish side of the periodic table, they tend to form ionic bonds. If it has a moderate electronegativity, like carbon, nitrogen, oxygen, phosphorus, those tend to form covalent bonds. And then if we have a higher electronegativity, Well, they have a choice. Well, actually, like oxygen too, it could form covalent bonds. It could form ionic bonds, chlorine, bromine, fluorine. It depends on what it's combining with. It depends on the difference in electronegativity between those atoms. Well, if there's a big electronegativity difference, we're going to have some ionic bonding. Ionic bonding is where we don't have any sharing of electrons. We have an electron hog and a pushover, someone who doesn't hold their electrons as much, and there's a complete transfer of electrons when we're talking about ionic bonding. The change in electronegativity, the difference between these two atoms, tends to be bigger than about 1.9. For example, we could look at sodium and chlorine on the periodic table. We can see chlorine has an electronegativity value of 3.0. Meanwhile, sodium has an electronegativity value of about 0.9, which gives us an electronegativity difference between these two atoms of 2.1, which is certainly bigger than our approximate 1.9 value. Therefore, we can predict that it's likely going to be an ionic bond. We can also see that sodium is a metal, chlorine is a nonmetal, and they tend to form ionic bonds. Nonmetal tends to form covalent bonds. We're bonding on the right-hand side of the periodic table. Okay, so we can look at the electron configuration of sodium. Its valence electron is in the 3s orbital, but it's not very electronegative. Chlorine, on the opposite side of the periodic table, has 7 valence electrons, and it is very electronegative. So it's going to say, sodium, you have that extra electron, and I want it. You're going to lose that electron, so you'll just be left with your noble gas electron configuration, core electrons. I'm going to gain that 1 extra electron, so that I'm 3s2, 3p6, and another way of writing that is that I now have a noble gas electron configuration like argon. We have a complete transfer of the electrons here. Notice we now have a sodium cation, it's fully lost an electron, and a chlorine anion. It's completely gained an electron. When we're talking about ionic bonding, we usually, and pretty much always, have millions or moles of ions interacting, attracted to one another as cations and anions. We can look at this structure here of sodium chloride. We have our sodium cation that's lost an electron, our chloride anion that has gained an electron. Notice that chlorine is an anion, it's bigger. Sodium has lost an electron, it's smaller. And it forms this beautiful lattice structure. It forms a crystal packing. And you can see for every green ball, we have a purple ball. For every sodium cation, we have a chloride anion. And this is a 3-dimensional crystal structure. So every cation is surrounded by anions. Every anion is surrounded by cations. If we tried to count all ions, it would be a really, really big number, but maybe that would be a good question with Avogadro's number. What we typically do is write the smallest unit. We can see these are in a 1-to-1 ratio, so we write this simply as sodium chloride, NaCl. That's just plain old table salt. The cation plus and the anion negative are attracted to one another through Coulombic forces. We know positives and negatives attract to one another. And we can calculate the force of that attraction between the cation and anion using Coulomb's law. Coulomb's law has a K value. It's just a constant, it's a number. And then, more importantly, it has Q1 and Q2 in the numerator. these are the charges of the cation and anion. So for sodium chloride, it would be +1 and -1. We kind of just use the absolute value. We don't really care about the fact that it's negative, but we have the magnitude of the charge for each one. We can see that if we had a +1, -1, that adds a 1 to the numerator. But imagine if it was a +2, -2. Now we would have a 4 in the numerator. As the charge increases, we go from +1 to +2 to +3 and so on, we can see that the force is directly proportional to the product of the charges. So as the charges increase, the force increases, which means the attraction between the cation and anion increases. That means that bond gets stronger, that ionic bond. Then in the denominator, we have the distance between the two ions. And this is directly related to how big or small those ions are. When we're talking about crystal lattices, of course, we're talking about compounds in the solid state. And most ionic bonding tends to be solid. Okay, so question. Suppose you're doing an experiment. You want a salt to maintain its crystal lattice structure. So that beautiful ordered structure where all the cations and anions are organized. Another way of saying that is we just want it to stay a solid to the highest possible temperature. Which of these salts would you choose? Chat with the person beside you. And 10 more seconds. And 3, 2, and 1. Okay, over half of us went for A, I agree, but we have a pretty nice distribution across the way. Sodium chloride has a melting point of 801 degrees Celsius. The other ones decrease from that temperature. You know what? I didn't know what their melting points were either, and I didn't expect you to have to Google them. And please don't memorize all the melting points of every compound. That'd be painful. But we can predict the ordering of these melting points based on Coulomb's law, which includes charges in the numerator and distance between ions in the denominator. We can look at trends using this formula, and we can predict which salt is going to have the highest melting point. Let's talk about how we're going to do that. Well, sodium chloride is made up of sodium cations and chloride anions. Potassium bromide, cation and anion. Rubidium bromide, a cation and anion. And cesium iodide, again, a cation and anion. That iClicker question directly brings us into this important example. In this question, we need to not just identify the compound that has the highest melting point, but we want to rank them from lowest to highest melting point And we can do that not by memorizing all their melting points, but using periodic table trends and Coulomb's law. Well, we can see on the left, each of these cations has a +1 charge. Each of the anions has a -1 charge. So the Q1 and Q2 for each of these ions is the same. I can't differentiate or predict the melting points by looking at the changing charges. Maybe a different problem I could, but right now I can't. However, these ions are different places on the periodic table, based on atoms in different places of the periodic table. And we know how to calculate the distance between these ions, or at least predict the trend. Here we have sodium, potassium, rubidium, cesium. As we go down the periodic table, we know those atoms get bigger. All of these atoms have lost an electron, so they're all going to be a little smaller than atom, but the trend is going to stay the same. As we go from the top to the bottom of the periodic table, the size is increasing. So cesium is going to be the biggest cation, sodium is the smallest. Well, then we can also look up chloride, bromide, and iodide, and see on the right-hand side of the periodic table, as we go down, the trend is the same. The ions are going to get bigger. Well, you can see the atoms are going to get bigger. Each of these atoms has gained an electron, so it's an ion. That makes it even bigger, but the trend is going to continue. So bromide is bigger than chloride, so on. So we can predict small cation, small anion is going to have a small distance between the ions, a small distance between their nuclei. And cesium and iodide, two bigger ions, are going to have a much larger distance between them. R, the distance between these ions, kind of like the bond length, is inversely proportional to the force. Bigger distances between the nuclei means that the force is smaller. Smaller distances between the nuclei means the force is going to be stronger. So smaller ions have stronger bonds. They have stronger attractions. And I want to show you my little words on the bottom, but I can't show you right now. If we have a stronger force, if we calculate a bigger force with Coulomb's law, that means we have a stronger attraction between those ions. How does that translate to melting point? Well, if we have a really strong attraction, you're going to have to put in a lot more energy to disrupt that attraction, to turn that crystal solid lattice into a liquid. We're going to have to disrupt those bonds a little bit. We have to put in more energy to disrupt that strong attraction. If we're putting in more energy, that means we need to increase the temperature more. We need to have a higher melting point to disrupt those bonds. We can see sodium and chloride are going to have the highest melting point because they have the greatest force. So we go back to the question. We want to rank these four compounds from lowest melting point to highest. So we now need to draw a conclusion. So cesium iodide, the largest, is going to have the smallest melting point. You don't have to put in as much energy. You don't have to crank the temperature. And this is all based on periodic table trends. Okay, so this gives us insight into how ionic bonding is happening. It's a give and take of electrons from something that's very electronegative. It pulls that electron versus the less electronegative ion that loses its electron. Well, ionic bonding is in contrast to covalent bonding. Ionic is that give and take. Covalent is when it's shared. Covalent bonds is when that change in electronegativity is less than about 1.9. Meaning we're forming bonds between atoms that have similar electronegativity values. We take a look at carbon and hydrogen. The bond between carbon and hydrogen is covalent. If we look at the electronegativity values of carbon, 2.5, and that of hydrogen, 2.1, we can see the electronegativity difference is 0.4, which is certainly less than 1.9. If we look at a bond between fluorine and fluorine, well, they're both very electronegative, but the difference between them is 0, which is certainly less than 1.9. A nonmetal bonded to itself is going to be a covalent bond on this side of the periodic table. Carbon to hydrogen is going to be a covalent bond. They're going to share those electrons. Well, just like people, some atoms are good at sharing electrons, some not so much. That electronegativity difference still plays a role in covalent bonds. Based on their electronegativity, we can see if they're good at sharing or if they still hog that electron density even in that shared covalent bond. When we come back next class, we're going to find out which atoms are better or poorer at sharing and how that results in polar and nonpolar bonds. Have a great day. I will see you next week.